Okay, so we're going to go over section 7.4 and we're going to look at logarithmic and exponential functions with other bases. So let's take a look at exponential functions first. So we're going to define exponential functions. With general basis. Right? And as we'll see, the same with the logarithm, these all come down to the natural logarithm and the natural exponential function, the e to the x, right? They're all just kind of essentially a reformulation of an e to the x and a ln of x. All right, so here we'll start with, we're going to define here with the base of an exponent. So we'll let b be an element of r plus. So this is just a positive real number. All right, and also b cannot be 1. Okay, all right. And again, the 1 to the x is just simply 1 all the time. So it's not an exponential, more like just a constant function. Right. So if this is true, right, b is any positive number and b that is not 1, then for all x element of the real numbers, b to the x is equal to e to the x ln of b. Okay, so if we notice here, this is the definition of an exponential, of base something other than e. Right, so when you think of 2 to the x, the representation of that is in terms of e raised to x times natural log of b, right? Whatever that base may be. Okay, so let's take a look at the function f of x, some of the properties. Of f of x equals to b to the x. Okay. All right. So again, now if you look at e to the x times ln of b, right? Ln of b is just some constant. So b to the x has the same properties as our exponential, right? In other words, the domain will be all real numbers. Right? And then the range, similar to the x, exponential is all positive real values, right? And again, that is directly from the exponential. Okay, and a couple of points on this graph here. We say, all right, b to the 0 is the same as e to the 0 times ln of b, and that is equal to 1. Right? In other words, f of 0 is 1. Okay. And another thing here, we have b is always greater than 1. Or sorry, if b is greater than 1, then the natural log of b is also positive, which means that this function is increasing. Okay, so for essentially like 1.5 to the x, 2 to the x, etc., bases that are larger than 1, we have that increasing exponential. Right? In other words, it looks something like that. Okay, now when b is between 0 and 1, then that tells me that the natural log of b is negative. All right, so that implies that b to the x ln of b is decreasing. All right, so it looks more like this. Okay. All right, so those are just kind of some basics of our general exponential, all right, with base b. Now let's take a look at some calculus, right? What is the derivative of an exponential, right? So let's say that I wanted to determine okay. Okay, so let's take a look at finding the derivative of this. So we wanted to find y prime is equal to the derivative with respect to x of b to the x. But now here, let's take a look at the definition of b to the x, right? As we scroll up here real quick, we define b to the x to be equal to this quantity here. So and I want to substitute because I know how to take the derivative of the exponential. All right. Okay, and now let's take the derivative here. The derivative of the exponential is the exponential itself, e to the x ln of b. Remember, ln of b is a constant. Chain rule says take the derivative of the exponent. Derivative of x is 1 times ln of b, so we are left with ln of b. All right, so that leads us to our following new derivative. Ln of b. All right, so that is our new formula for the derivative. And here, based on this, if this is true, then I should also, excuse me, let me actually write it in that form, right? Where e to the x times ln of b is b to the x. So let me write it in that form. Okay, now this also leads us, now I know what the antiderivative of b to the x is. Right, so that means that based off of this, the integral of b to the x dx is going to be equal to 1 over ln of b times b to the x, and again, don't forget the plus c. Okay, so now we have those two formulas for the derivative of the general exponential and the integral of the general exponential. All right, and then similar to some other properties here of the exponential, similar to the natural exponential, is all of those exponent properties still hold. Right, so other properties. We have b to the u times b to the v is still b to the u plus v. And then b to the u raised to the v is equal to b to the u times v. All right, and then the division one, we have is equal to b to the u minus v. All right, and then some other properties here, ab to the u, a to the u, b to the u, and a over b to the u is a to the u over b to the u. Right, so again, these are all the exponent properties that can be derived from the natural exponential, right? They also apply to a general exponential of base b. Okay, all right, so and again, what this is kind of leading us to these exponents is before, at least in Math 1, we talked about these rules applying to only rational exponents. But now this is an extension here saying that because of the nature of the exponent and the domain of the natural log is that these exponent rules apply to all real numbers, right, including irrational exponents. All right. Okay, So, and again, what that means is now we can say, all right, I can if I have something like this, here the x is in the base, so I use the power rule, and general power rule just says, all right, this will be x to the pi minus 1. All right, so we make this extension into irrational exponents. And again, an irrational exponent, you can think of it in terms of it's some kind of logarithmic operation. Okay, so now we looked at these general exponentials. Let's take a look at logarithms. Okay, so we have y is equal to e to the x. And again, this is true if and only if x is equal to natural log of y. Again, that is just our definition here of the exponential and how it's related to the natural log, its inverse. So now let's look at the general form. Let's say that y is equal to b to the x. Okay. And then also here we have, let me take the natural log of both sides here. Actually, excuse me. Let me take a step back here. All right, so the general exponential is this. And one thing that we realize here, since it is an e to the x, that this is a one-to-one function. All right, because again, b to the x is simply just another representation of e to some power. Okay, so if that's true, that means that there is an inverse, right? So we want to find out, all right, what is the inverse of the general exponential? Okay, so to do that, we say, okay, so again, let's use the same kind of techniques here. We'll say, all right, switch out the x and the y. All right, and now let's solve for y. Okay, all right, so we'll take the natural log. Of b. And solving for y here, quickly we get y equals to natural log of x over natural log of b. So this is our inverse. All right, so if what this is telling me here is that if f of x is equal to b to the x, then f inverse of x is equal to natural log of x, natural log b. All right. Now, if you recall kind of your study of logarithms from any other course, this should look a bit familiar, right? This looks like the change of base formula. All right. So in general, when we see any logarithm that is not the natural logarithm, it is simply a ratio of two natural logarithms. All right. So now we're going to define here. All right. Define for any base b greater than 0. And again, b not equal to 1. And again, because that would make the inverse invalid. And again, we won't be dealing with an exponential at that point. It would be more of a constant function. So we're going to define here this ratio. Since it shows up a lot, we just give it its own name. So, and in fact, what that name is a log of base b. All right, so we're going to define log base b of x to be equal to the natural log of x over the natural log of b. Okay, so when we think of any other log that is not base e, we can always think, oh, that is just a ratio of two natural logarithms. All right, and that is the inverse of the general exponential. All right, so let's take a look at the inverse relationships here. All right, and again here, if this is true, if y is y the function log base b of x, this is true if and only if x is equal to b to the y. Okay. All right, so now let's take a look at the inverse relations.
That's incredible.
For exponential and logarithmic functions. Okay, so let's say b greater than 0, and again b not equal to 1, then b raised to the log base b of x is equal to x, and again this holds for x greater than 0. All right, and then log base b of b to the x, that would be equal to x. And again, this is for x being any real numbers, right? And again, these are compositions, so the x has to be, make sure that it's in the domain of the inner function. In this case, when it's the logarithm, it must be positive. And in the second one, the exponent of b can be any real number. Okay, so if we think of the log base b of simply a ratio of two natural logarithms, that means that it follows that the domain and range is very similar to the natural log domain and range. So some properties here. Let's say, okay, the domain properties of log base b of x. The domain, similar to the natural log, is all positive real numbers. And then the range is all real numbers. Okay. All right, and again here, similar to, since it is a all right, since it is a natural logarithm, it does have this general shape. All right, I can see the domain and the range kind of shown there on the graph. Okay, and similar when we had the exponential, if this is true, that means that based on the inverse relationship, that any log of whatever base of 1 will always be 0. Okay, and for values when b is greater than 1, log base b of x is increasing. All right, in other words, it looks something like that up there. And that means when b is between 0 and 1, then log base b of x is decreasing. That means that it looks more like this. All right. Okay. So now we went over the basics of our log base b of x. So now let's look at just some general calculations, right? Regular derivatives and integrals. All right. So let's say that I want to find y prime of log base b of x. Okay. So let's use again, right? Let's kind of change it to something that I do know how to take the derivative, right? So if this is true, all right, so this is true, again, if and only if, with the inverse relationship, if that's true. So now let's take the derivative with respect to x of both sides here, right? So we're going to take dx All right. Now, one thing to notice here is the y is a function of x, so we're going to use a chain rule along with the implicit differentiation on the right-hand side there, right? The left is easy, right? That's the independent variable x, so that is 1. On the other side here, the derivative of b to the y is ln of b raised b to the y. And again, that's something that we covered earlier in this section. Chain rule, right? Says, okay, well, what is the derivative of the exponent here? And then that would be dy dx, or y prime. All right. Okay, and then solving for dy dx or y prime, we get dy 1 over okay. So we have that to be our derivative, and again here, b to the y, let's kind of, what is y equal to? Log base b of x. All right, and again, using the inverse relationship of the exponential and the log, that means that this is 1 over x times ln of b. All right, so now we found the derivative of log base b of x is equal to 1 over x times ln of b. All right. Now, in applications, so notice here that we restrict our values x to be greater than 0. What is also true is we can think of, to kind of make an extension to some of our applications, we could say, all right, sometimes it is defined 1 over x ln of b. And again, here this works for all non-zero values of x. Okay. So that's the definition of the derivative. Notice there's no, well, we could define it, but the books normally don't define the integral of just the general logarithm. And the reason being for that is that, well, it's just a natural logarithm, right? we could say when we have something like this. All right, if you look at this, remember if we have something like this, right, I mean, it won't be incorrect to say log base b of x, but normally what we would do, since ln of b is a constant, we could factor it out, and then we can right now we can do that. That's ln of x, and notice here that we get back there log base b of x plus c. Okay, so we don't need to remember any extra formula or refer to any extra formula. We can just think 1 over x would always just be a natural logarithm. Okay. All right, so let's wrap this section up by doing a couple more examples here. So let's say, how about some examples. The integral over x squared dx. Okay. All right, so here let's practice using a substitution, right? Looking at this again, as you work through these new examples, remember if the variable is in the exponent, that is not a power rule, right? Do not use the power rule. This is some kind of exponential that needs to be used. All right, so let's start. A good way to start here is just let u be whatever the function in the exponent is, and see what it goes from there. All right. So this may work, right? In this case, I think it will work, but sometimes it might not work. I might have to start again. But let's just start from here. All right, u is 1 over x, so du is negative 1 over x squared dx, which I see right out there, right? The 1 over x squared. The only thing I don't see is the negative. So let me multiply that to both sides, all right? And then we can go from there. All right, so now let me substitute here. We get negative, excuse me, grow 10 to the u du. All right, so now this worked out well, right? Now we just use, this is a basic base b to our variable. So applying that formula here, and we get negative over ln of 10 to the u plus c. Oops. Let's change everything back to the x variable. 10 to the 1 over x, yes. Okay. Let's see, let's try one more here about okay. So here, how about we find let's do a derivative one. Let's say find y prime for y equals to log, let's see, base 3 of x over x. Okay. Excuse me. All right, so let's take a look here. So let's take y prime equals to, and again, we're gonna, if we want to use the quotient rule here, we'll say, all right, x squared. All right, and then in the numerator, we'll say the derivative of the log, which I know is 1 over x ln of 3. Leave the x there. and then minus, leave the log base 3 of x, and then times the derivative of x, which is just 1. Okay, and now let's clean this up a bit. So one thing when you submit answers to me, I don't want any complex fractions. In other words, I don't want that 1 over ln over 3. So let's start trying to simplify that. So here, notice the x simplifies to 1. So we're just left with 1 over ln 3 minus, and now I'm going to write this as a natural log, as a ratio of 2 natural logs, excuse me. And then let me now get rid of the complex fraction. Multiplying the top by ln of 3 leads me to the expression 1 minus ln of x, and in the numerator we have x squared times ln of 3. All right, and that is the derivative of that function. All right. Thank you. This concludes 7.4.